Hey guys, the objective of this video is to discuss the shear box test, and then we're going to do an example to find the friction angle for undrained and the coefficient for an undrained test. So the shear box test, the way it works, just very simply, I'm not going to go into the specifics, is we have two boxes which are aligned one on top of each other, and we have our sample of soil inside these boxes. And what we do is we come to our boxes and we apply a normal stress, so that would be a force, but because it's acting over an area, it's a normal stress, and we apply a shear stress. And what happens is that this box will slide. So this lower box will slide this way and this way. So they'll slide past each other, causing shear stress and normal stress inside our box. So what happens with the shear box test is we have a predetermined failure plane. So we've decided that the failure plane we're looking at is this plane here. So that's the plane it fails on, which is different to the triaxial test, which you're going to discuss in a bit. But for a shear box test, we have two boxes which are aligned. We apply a shear stress and we pull it, which creates a shear stress. As they slide past each other, the soil will eventually fail, and that'll tell us the normal and shear stress at which it fails at. So if we were to draw a small graph showing this, we would have the strain against the shear stress, and it would look something like this. We would get to a point and it would fail, and that would be the shear stress it fails at. What would this look like if you would actually witness this? What would happen is you'd have your two boxes, you'd pull them, it would resist, and then eventually it would just give way and slide, and that would be the shear at which it fails at. So the first thing we need to do is develop something called the Mohr Coulomb criteria for failure. So the Mohr Coulomb criteria for failure says that the shear stress equals the cohesion plus the normal stress times by tan phi. So this equation relates the shear and normal stresses to the cohesion and the phi value, the frictional angle. You can think of this as y equals mx plus b. So y is the shear. We know that we can represent gradient by tan of the angle, which means that x is sigma n, and the cohesion is the y-intercept. So this is the same as y equals mx plus b, which is going to be very handy in a second. So if we were to do this test, let's say we got the following values. So we did test 1, 2, and 3, and we got normal stress at failure. So we're always concerned about failure. Let's say that we were applying 100, 200, and 300. So those are the stress values we applied, and let's say we got this shear stress at failure. So the shear stress at failure, let's say the values we got were 97, 138, and 182. So a question you might be asking is, how can we get different normal stresses and shear stresses? Surely they would only be one value at failure. But we know that friction, so one component of the shear stress failing is friction, this angle of friction. And we know that friction is a function of the normal force. So we're going to get different shear stresses at failure for different normal stresses, because part of the failure criteria takes into account friction, and friction is dependent on the normal force. If we increase the normal force, we're going to increase the shear stress at failure. So let's say we now want to find the values. Okay, so let's say that this test was an undrained test. So this was undrained, and we want to find the cohesion undrained and the angle of friction undrained. So those are the two values we want to find. So what we would do is we could solve this example two ways. The best way, in my personal opinion, would be to draw a graph to scale. So if I were to get a nice piece of paper, so I would have, and this has to be to scale, otherwise it's not going to work. So I would have 100, 200, and 300, and this would be my normal stress, and we would have on this axis the shear stress, which has to be the scale. So I'm using increments of 4 centimeters to represent hundreds. So that would be 100, 200. A good idea would be to dash in 25s, just because I'm going to be looking at those values. So we would come to this graph and plot on all our points, and this of course is the shear stress. So we have 197. So 197 would be around there. We have 200, 138. So 200 and 138, that's 125. So 138 is around there. And 300 and 182. So 300 and 182, so that's 175. So 182 is around there. And what we would do is we would draw our graph. We would connect all these points as best as we can and get something which looks like that. Now, as I said, this is the curve tau equals c plus sigma n, sigma n tan phi, and because we're doing effective, this sigma c is effective and this is also effective. So what we would do is now find these values. So we want to find, as we said, this is the same as y equals mx. So this would be y equals b plus mx. So we know that m can be represented by tan phi. So all we're going to do is we'd literally come with a protractor and measure the angle. So this one, so we'd come and measure this angle, which would be around, if we measure that angle, around 22 degrees. So that is phi. So phi undrained is equal to 22 degrees. And we would look at the, we know that C dash is given, sorry, this is Cu and phi u. Sorry, we're doing undrained. That's not dash, that's not effective. We're looking at the undrained properties. That's what we had in the question. The question asked for undrained, which is C subscript u and phi subscript u. So C subscript u and phi subscript u, so that would be phi u, which would equal 22 degrees. And we said that the coefficient undrained is the same as b, which we know is the y-intercept. So we would come to our scale graph and just see where it intercepts, and it intercepts at around, say, 55. So our Cu equals 55. That's how I think you should solve the question. If you really want to do a very technical way of doing it, because I know engineering students like to be very technical, you could find the gradient. So we know that we know the gradient is the same as tan of the angle, and we know that we could find the gradient by doing rise on 1, which is y2 minus y1 on x2 minus x1. So we could find that to be 138. So 138 minus 97 on 200 minus 100, which is the run, which means that phi equals inverse tan of 138 minus 97 is 41 on 100, and we would get around 22 degrees. So we'd get a similar answer. We could then find the y-intercept. We know the equation for a line is y minus y1 equals m outside of x minus x1. We know that m equals tan phi, which means we could find our gradient. Tan would equal tan 22, which would equal around 0.4. So we could find our gradient because we know the angle now. And we know a point would be, one of the points we have is 197. So we have the point 197. So we could use this information to find the equation. So it'd be y minus 97 equals 0.4 outside of x minus 100. So just subbing in the point and the gradient, we could get this equation, and we could have y equals 0.4x plus, this would be 0.4, so minus 100 by 0.4 plus 97 is 57. And because y equals mx plus b, we know this equals tau equals 0.4. X is the normal stress plus 57. And now we want to know where this cuts the y-axis, the y-intercept. So we're going to look at when sigma n equals 0. So we would get that tau equals 0.4 outside of 0 plus 57. So tau equals 57, which means that Cu equals 57 because we know Cu is the intercept. So we can see that's 57, which is pretty similar to 55. So you can answer this question graphically or algebraically. You can see the algebra is a little bit of a pain. I don't think it's that necessary. I think the graphical method is a lot better. So once again, just to summarize what we did, we talked about the shear stress. we talked about the shear box test, which we can find the normal and shear stress on a predetermined failure plane. We then saw the Mohr-Coulomb criteria for failure, which links the shear stress and the normal stress to the cohesion and the angle of friction. We saw that this is the same as y equals mx plus b. We did a test where we had normal stresses against shear stresses, and we said that as we increase the normal stresses, the shear stresses increase because it's dependent on the friction. We then drew a graph of normal stress against shear stress. We measured off the values for phi u and cu, and then we could have found it also by doing a more technical approach by using gradients and y-intercepts. As you can see, the graphical method is a lot simpler. Anyway guys, hope that helps.